we present FrontierNet, learning visual cues to explore. FrontierNet is an autonomous robot exploration system. It uses a learning-based model to propose visual frontiers and predict their information gain from individual images captured during navigation. Frontiers are a common representation used by autonomous robots to guide exploration in unknown environments. It represents the boundary between known and unknown space. The robot moves toward frontiers to gradually expand its understanding of the environment. Most existing methods extract frontiers from a dense 3D map, such as an occupancy grid. These methods rely heavily on the mapping process, and more importantly, often overlook the rich visual cues available for inferring frontiers from image appearance. We observe that humans can easily identify potential areas to explore from a single image. Can a robot also detect frontiers directly from visual cues? To achieve this goal, we train a model that takes an image as input and predicts pixels that likely correspond to frontier regions in 3D. At the same time, the model learns to predict the information gain of each pixel, indicating how much unknown space could be observed from that region. Our system anchors these predictions into sparse 3D frontier points in the scene. In practice, we enhance both the model and the anchoring process using monocular depth priors inferred from the RGB image. Next, we explain the anchoring process in more detail. We begin by obtaining 2D frontier predictions from the model. Then, we compute the gradient directions of the depth prior. For each frontier pixel, we construct a feature vector that includes its pixel location, the corresponding depth gradient direction, and predicted information gain. We then apply a clustering algorithm to these features to obtain sparse 2D frontier points along with their directions on the image plane. For each 2D frontier, we use its centroid pixel to estimate depth. In general, a 3D frontier lies in the free space between the foreground and background. To approximate this, we sample two depth values along the positive and negative directions of the depth gradient at the centroid and take their average. Through this process, we obtain a reliable abstraction from 2D frontier predictions to 3D frontier representations. For planning, we maintain a sparse graph that includes downsampled historical robot poses and frontier camera visibility correspondences, optionally incorporating a 3D map. To plan a path to the next goal frontier, the robot retrieves its corresponding visibility edge, samples 3D locations along it, and performs path planning toward the first sample that lies within the 3D map. Once it reaches that point, it continues moving toward the frontier. When a 3D map is not available, the robot actively performs visibility checks using the depth prior along the edge and navigates to the closest visible point to the frontier. Our approach leverages both appearance and geometric information from images to predict frontiers and estimate their information gain. It enables highly efficient autonomous exploration across diverse environments, including complex multi-floor scenes. By making frontier detection independent of 3D mapping, we reduce its reliance on heavy map processing and also show that semantic visual cues helps information gain estimation. While our system can optionally use a 3D map to enhance exploration in dynamic gain adjustment and path planning, it also works effectively in a completely map-free setting. This improves memory efficiency and makes the system suitable for general-purpose navigation tasks such as object search. We also compare our approach with several baselines and find that it achieves the highest exploration efficiency, especially during early-stage exploration. This is mainly due to its more accurate estimation of information gain. Additionally, because our frontier detection process is decoupled from the 3D map, the system is more robust to noise and artifacts in the map, which often mislead other approaches. We also validate our approach in real-world experiments with a legged robot exploring an indoor environment using FrontierNet. The robot uses the RGB camera on its end effector and autonomously explores the entire floor without manual intervention. Thank you for watching. More details and results can be found in our paper.